Okay, so now we start with the questions for the chapter Electromagnetic Induction, and we'll look at some good questions now, so that we can major of the concepts and catches of the chapter can be covered in the major tricks. So here comes question number 1. It says, calculate the flux through square loop placed at distance x from the wire, and you could refer to the figure below. That is what क्वेश्चन कह रहे हैं तुम्हें कि हम लोगों को एक स्क्वायर लूप दिया हुआ है जो कि x डिस्टेंस पे है एक गिवन वायर से, और हमें स्क्वायर लूप से फ्लक्स निकालना है. सो बेसिकली यू सी दैट यू आर गिवन अ कांस्टेंट एरिया. सो लेट्स सी हाउ टू प्रोसीड इन दिस क्वेश्चन.
See, because of this wire, there is some magnetic field which is induced in space.
That's right.
And we can calculate the direction of magnetic field.
Right.
By the right hand thumb rule. See, by placing the right hand thumb over the direction of the current and by swirling the fingers around, you could get a direction, right? Here you will get in this sense. So the magnetic field will be induced in this direction. So regarding this plane of paper, the magnetic field will be perpendicular to the plane of paper protruding inside. Here the square loop is placed at a distance x from the wire, right? Now the magnetic field will be B, right? And this B will not be constant. This will be varying with respect to distance. The B at a distance x from the wire would be mu naught I by 2 pi x. This would be decreasing with respect to the distance. So if we take a small area at a distance x from the wire and of width dx, this area would be x into a into dx.
Exactly.
And the flux linked in this area would be B at this point, B of x into a into dx.
That's right. That's right.
Now this flux will be varying with respect to this distance from the wire. So we are going to calculate the area. Now we are going to calculate the flux for the area of the square loop. That is nothing but we are going to integrate this function from x to x plus a.
That's right.
So what we are going to do is we'll take another function, right? We'll change this variable to b because it gives us confusion, because I have informed you that x is distance from the wire.
That's right. That's right. Basically we see that a correct application of principles of integration is very important in such chapters, especially not only in electromagnetic induction. There are some other chapters also which use a great deal of integration, and if you're not good with the rules of integration, you can't really deal with such questions, and obviously such a chapter becomes a burden in that case.
This is a function of x, right?
Right.
So the flux varies with respect to the function of x. So I am going to integrate this over this area, that is nothing but from B to a plus b.
That's right.
And this would give me the flux linked with the entire coil, and this, on integrating this, we will get, first I am taking the constant outside the integral. This is a simple integral, right?
That's right.
And integration of dx by x will give us ln x. So it is nothing but, as I am integrating from b to b, I will get ln a plus b minus ln b. I hope you are familiar with these concepts.
Exactly. We need to also be thorough with the concept of log here, which gives us the formula mu naught Ia by 2 pi into log of a plus b divided by b.
And finally we will get the answer as this. mu naught IA by 2 pi into ln A plus B by B.
Exactly. So basically this is a conceptual question, and what you need to pay concentration here is that when the distance is going to remain constant, when it is going to vary, where in which direction are you going to take dx, all that matters a lot. Okay, and the direction of b that you're going to take, such, because it can just affect your sign and eventually your answer. And lastly, you should also be clear with the concepts of integration. So this was question number 1 for calculating the flux through a square loop. We'll shortly be looking at question number 2 now. Basically, okay, now we come to question number 2. It says that given a magnetic field is the given magnetic field is varying with time in space, and we are given B is equal to KT, and the direction of it being into the plane of the paper. We have to calculate the EMF developed in the ring of radius r placed on such a magnetic field. Basically हम लोगों को एक magnetic field दी है जो कि टाइम के साथ वैरी कर रही है, और टाइम के उसमें उसका फंक्शन दिया हुआ है k into t, एंड उसका डायरेक्शन दिया हुआ है हमें into the plane of the पेपर, और हमें EMF निकालना है जो कि रिंग में डेवलप हो जाएगा ऑफ अ रेडियस r, जो कि एक ऐसी वैरिंग मैग्नेटिक फील्ड में प्लेस की गई है. सो ऑब्वियसली वी सी, एज वी हैड सेड बिफोर, दैट EMF is produced, generated only if there's a change in magnetic field, and here we know that magnetic field will keep on varying with time, and that is the reason EMF will be developed. So just let us look at how we are going to solve this question.
I said you earlier, right? Now first we know that the flux linked with this particular ring. What is the flux linked with the particular ring is nothing but B into pi r square. I have solved this question earlier, deriving the flux linked with the ring placed in a uniform magnetic field. But here the magnetic field is varying. Magnetic field at any time t is given by k into t. So at any time t, the flux linked would be kt into pi r square. So the flux is varying. So
That's
if the
right.
flux is varying with respect to time, there will be EMF produced, right? So I am going to calculate the EMF produced because of this varying flux. See, what is the EMF? I have said you about a formula. The EMF produced will be nothing but minus d phi by dt. Is nothing but the flux is increasing here in the inside direction. That is nothing but the anti-clockwise direction.
That's right.
So the EMF developed will be in the clockwise direction here.
Right.
So I am going to differentiate this. I will get k into pi r square.
Right. We just t will be removed.
It's a simple differentiation.
So basically we see that this was another simple question. The catch here was that the flux in this case is not constant. It varies with time, and we should be knowing how to solve such questions, and it was basically a conceptual question. So this was question number 2. We now come to question number 3. It says, calculate the EMF developed in the given below wire loop being moved from a region having uniform magnetic field to a region not having any magnetic field. We have to refer to the diagram below. Basically question कह रहे हैं कि हमें EMF निकालना है किस चीज़ का. एक नीचे एक वायर लूप दिया हुआ है जो कि एक रीजन से दूसरे रीजन में ले जाया जा रहा है. एक रीजन में यूनिफॉर्म मैग्नेटिक फील्ड है और दूसरा वाला डज नॉट हैव एनी मैग्नेटिक फील्ड. सो डायग्राम हमें दिया हुआ है, एंड वी आर गिवन दैट द मैग्नेटिक फील्ड इज पॉइंटिंग into the plane of the paper. So let's see how to proceed with the questions.
See here the wire, the closed wire is moving from the region of having a where one region is having a magnetic field B and the other region is not having a magnetic field at all. And the flux linked with the coil will be only because of the region having the magnetic field B.
That's right.
We'll divide this particular wire into two segments.
Okay.
Where one segment is in the magnetic field B and the other segment in the other region where there is no magnetic field.
Okay.
I cut this loop into two parts so that you could understand. And because of this part, there will be no flux induced because there is no magnetic field in this region. But in this region, there is magnetic field, right? So because of this magnetic field, there will be flux linked in the coil. So the total flux linked in the coil at any time would be only because of this region present in the magnetic field.
That's right.
Let us assume that at any time x length of the wire is placed in the magnetic field and the A minus x is outside the magnetic field. Flux at any time would be given as B into area of the region which is present in the magnetic field. That is
Right.
nothing but A into A minus x.
Okay.
Now what is happening is we are moving this out of the magnetic field, right? So with some particular velocity. So the flux is going to change with respect to time.
That's right.
So this rate of change of flux with respect to time is going to be the EMF developed.
Right.
So the EMF developed would be minus d phi by dt. This is nothing but B into A minus x by dt.
Right.
We will get as B into A into dx by dt. And this dx by dt is nothing but V because it is nothing but the increase in velocity.
Right.
So the EMF developed is nothing but BAV. And see here, the flux is continuously decreasing. So the flux linked with the coil is in clockwise direction, anti-clockwise direction. So it is continuously decreasing. So the EMF induced will also be in anti-clockwise direction
Okay.
to
So
increase the change.
So basically we see that in this question we were not given the values of many things. We were just simply given a square loop and a uniform magnetic field. So basically we were to leave the answer in terms of B, A and V. Okay, so this was question number 3. Coming on to question number 4, it says, calculate the EMF induced in the ring and the energy dissipated in one complete rotation. The resistance of the ring is given to be capital R and the radius is small r. We could refer to the diagram given below. Basically हमें इसमें EMF निकालना है रिंग का जो इंड्यूस होता है रिंग में एंड कितनी एनर्जी एक कंप्लीट रोटेशन में डिसिपेट हो जाएगी यानी निकल जाएगी उससे. हमें रिंग की रेजिस्टेंस कैपिटल आर और रेडियस स्मॉल आर दिया हुआ है. सो हाउ विल वी प्रोसीड विद द क्वेश्चन?
See, if the ring is always perpendicular to the magnetic field, the flux induced will be, flux developed in the ring would be B into pi r square. We already know that, right? But if the ring is moving out of the plane, the B dot A would be changing because flux is nothing but, flux is only maximum when the area is perpendicular to the magnetic field.
Exactly, that's the most important point.
But here what happens is the ring is moving out of the plane of the paper. Let me consider that at any time t the ring would have rotated by an angle of omega t, right?
Right.
So I am drawing a vector diagram of the area. Initially the area is pointing outward in outward direction, right?
Okay.
At any time t, the area vector would make an angle of omega t.
Right.
So it's in the opposite direction.
That's right.
At any time t, the area vector would make an angle of omega t with b vector. So at any time t, the flux linked with the coil would be B dot A. That is nothing but B into pi r square into cos omega t.
That is the area basically, pi r square.
So initially at time t equal to 0, this is placed perpendicular to the magnetic field. So at that time the flux length is maximum, but is gradually decreasing on, because the ring is rotating and it is moving out of the plane of the paper.
That's right.
So because the flux is changing, obviously the EMF would be developed inside.
Right.
In the ring. So the EMF developed in the ring would be minus d phi by dt. That
True.
is nothing but, if you differentiate this, we will get as b pi r square omega sin omega t. That is nothing but pi r square b omega sin omega t. This is the EMF induced at any time t. Even the EMF induced is also a function of time.
That's right. So basically, we found out here the EMF in terms of sin omega t, that is pi r square b omega sin omega t.
And again, I gave you another part in this question. We are going to calculate the energy dissipated in one complete rotation. See, at any time, I have given that the resistance of the ring is R.
That's right.
Let me change. Okay, I have used the radius as small r. Okay, I will change the radius to capital R and the resistance to K. So, at any time t, the current in the coil would be pi r square b omega sin omega t by K. Right?
Right.
So at any time t, the power dissipated would be V dot I. That is nothing but multiplying these both values. You can also write this as I square K.
That's
so
right.
the energy dissipated in one revolution we can calculate by the power method. The energy dissipated in one revolution can be written as integration of p dt from 0 to 1 revolution. That is nothing but a time period of this rotation. That is nothing but 0 to 2 pi by omega I square k dt. This is nothing but 0 to 2 pi by omega pi r square b omega whole square sin square t omega t.
Right. So basically, we just use the formula for power. Okay. Power being the voltage into the current, or the current square into the resistance, and then we used in terms of integral and in the power term, and multiplying it with dt, we got the energy. And we are doing this as we have to find the energy dissipated total in the process.
I am calculating the power energy dissipated finally.
Okay.
If finally solve this integral, we will get the value of this integral is nothing but 1 by 2 omega.
That's right.
So finally the answer would be pi square r power 4 b square omega by 2k.
That's right. So basically, we see that this was our answer to the question. The question seemed to be a technical and a conceptual one. It was not very difficult, just you need to be careful with the values and with the what formula and what concept you are to use at what time.
Probably these are the questions which the IIT JEE people will target.
Exactly. So this was question number 4. So question number 5 says calculate the EMF developed in the rod present in the below diagram. Basically हम लोगों को एक रॉड दी हुई है, उसकी एंगुलर वेलोसिटी हमें ओमेगा दी हुई है, उसकी लेंथ दी हुई है हमें a, and b being the magnetic field it goes into the plane of the paper, and हम लोगों को इस रॉड का EMF कैलकुलेट करना है. Let's see how we'll proceed in it.
I'm going to solve this question based on the motional EMF concept. Here, let me consider a simple diagram of a rod. Let me take a small part of a rod at a distance x from one of the end.
Okay.
Let me consider dx part of it. And the velocity of this dx part of the rod would be omega into x, right?
Right.
Because the angular velocity is omega, the velocity of the particle at a distance x would be omega x.
That's right.
And for this small part of the rod, dx part of the rod, the EMF developed would be dE would be V cross B dot dx.
That's right.
V is always in the plane of the paper, but B is out of the plane of the paper. So V and B are always perpendicular. So V and dx will be always along the direction of the rod. So V will be perpendicular to B and V cross B will be always parallel to dx. So we'll get VB dx. Because of a small part dx, small dx part, the EMF induced will be this much. And velocity is a function of distance. So this because of this, what happens is the EMF induced can be written as B into omega x into dx. So this
That's
is a function
right.
of x. So the EMF varies with respect to the distance of the small particle dx. So if it is placed at if the dx is located near the end, then it would be EMF developed by that small particle would be less. And the similar way, if it is placed near the other end, the EMF developed in the small part dx would be more.
Exactly. So this was the concept of motional EMF.
And we are going to integrate this from 0 to L to the entire length of the rod. So the EMF developed would be B omega. I am taking the constant outside first. X dx. This is a simple integral. On solving, we will get it as B omega L square by 2.
So basically, okay, yeah, we see that we use the concept of motional EMF in the question. So actually it's not necessary to always use the standard method of that flux and thing, because it's sometimes not really favorable, and sometimes when we see that our object is in motion, or it's the rules are basically not getting valid, we use the concept of motional EMF. It is shorter and also gets done quickly and more accurately.
It depends on the problem. Some problems are easier to solve in flux method and some are easier to solve in this method.
Exactly. So you just need to identify the question and you need to see that what method you have to choose that would be best for the given question. So this was question number 5.